There are moments in astronomy when familiar language begins to soften, not because understanding has failed, but because what is being described no longer fits comfortably inside words shaped by ordinary experience. Terms like large and massive still apply, yet they feel strangely light, stretched across something that resists intuition. Black holes are no longer uncertain objects. They are measured, modelled, and observed through their influence on stars, gas, and light. Their existence is settled. Their behaviour follows known physical laws. In many ways, they are among the most solidly understood structures in modern astrophysics, and yet even within that clarity, scale introduces something quieter and harder to resolve. Most black holes fall into ranges that, over time, have become familiar. Stellar mass black holes form from collapsing stars and remain locally influential. Supermassive black holes reside at the centres of galaxies, weighing millions or billions of times more than the Sun, shaping the motion of stars and the flow of matter across immense distances. They are powerful, but expected. They fit. As more of them are studied, patterns emerge, typical masses, predictable relationships. A sense of proportion develops, even at cosmic scale. Astronomers learn what to expect, where the boundaries usually lie, and how far those boundaries tend to stretch. Then, occasionally, something appears that does not sit comfortably within those patterns. Not because it violates the rules, it follows them exactly, but because it occupies a region of scale where comparison begins to thin out, where familiar reference points lose their usefulness, where numbers remain precise yet meaning becomes harder to hold on to. At extreme mass, gravity no longer feels like something acting on objects. It begins to feel like a condition of space itself. Motion adjusts, light responds, time behaves slightly differently. Not violently, not dramatically, simply, inevitably. Astronomy is careful with words like largest. They are never absolute, always bounded by what has been observed so far. The universe is vast and observation is incomplete. Larger objects may exist beyond detection, beyond clarity, beyond reach. Science does not pretend otherwise. And yet, within those limits, separation still matters. Among the many supermassive black holes that have been measured, there is one whose estimated mass stands far apart from the rest. Not by a narrow margin, not by rounding or revision, but by a difference large enough that it quietly reshapes what comparison even means. This realization did not arrive with spectacle. It emerged gradually, through careful analysis of light that began its journey billions of years ago. Through measurements refined, revisited, and tested against multiple methods. Through an object first recognized for its brightness, then for what that brightness implied. What makes this object striking is not only its mass, but when that mass already existed. The light used to study it left its source when the universe was far younger than it is now, when galaxies were still assembling and cosmic structures were still settling into place. Somehow, by that point in time, this black hole had already grown to a scale that challenges comfortable timelines. The mechanisms that allow black holes to grow are known. Matter falls inward. Black holes merge. Dense environments accelerate accumulation. Over immense spans of time, mass builds. None of this is mysterious on its own. And yet, when applied here, those same mechanisms are forced to operate near their limits. This does not represent a failure of physics. It marks a boundary of detail, a place where the broad outline is clear, but the exact sequence remains under study, where understanding exists but not yet completeness. The object itself does not announce these tensions. It does not flare or threaten. It remains distant, anchored to a quasar whose light has crossed deep time to reach us. Its significance lies not in drama, but in scale. In how far it sits from every other measured example. Among all known black holes, one occupies a category almost by itself. If you enjoy these videos, please consider liking and subscribing. Any support is appreciated, so settle in and follow the traces that lead to the most massive black hole ever discovered. Black holes are often spoken about as though they are exotic exceptions, strange interruptions in an otherwise orderly universe. In reality, they are the natural outcome of gravity doing exactly what it always does, following the same rules it follows everywhere else, simply pushed to an extreme that feels unfamiliar. In modern astrophysics, a black hole is not defined by darkness, destruction, or even disappearance. It is defined by mass. More specifically, by how much mass has been compressed into a given region of space, and what that concentration of mass does to space-time around it. A black hole is not a hole in the ordinary sense. Nothing is missing. Instead, something has become so dense that the structure of space itself curves inward, creating a boundary beyond which escape becomes impossible. This boundary is known as the event horizon. It is not a physical surface. There is nothing solid there. It is simply the point at which gravity becomes overwhelming enough that even light can no longer travel outward. Inside that boundary, all paths through space-time lead inward. Outside it, the universe behaves much as it always does. What matters most is not how large a black hole looks, but how much mass it contains. A black hole with a relatively small physical size can still exert enormous influence if its mass is concentrated enough. Conversely, a black hole with a very large event horizon may appear visually vast, yet its gravitational pull at a distance depends entirely on the mass inside, not the width of the boundary itself. This is one of the first places intuition begins to slip. Size feels important because it is how humans normally judge scale. But in gravity, mass is the true currency. Mass determines how strongly space-time curves. Mass determines how objects move nearby. Mass determines how light bends, how time slows, and how energy behaves in the surrounding region. Because black holes emit no light of their own, they are not detected by direct observation. No telescope sees a black hole itself. Instead, astronomers detect what happens around it. They observe stars whose orbits curve too tightly to be explained by visible matter. They measure gas clouds accelerating to extreme speeds before vanishing from view. They study disks of superheated material spiraling inward, glowing intensely as friction and gravity convert motion into radiation. In many cases, it is this surrounding light that gives black holes away. Matter falling toward a black hole does not disappear quietly. It heats up. It compresses. It radiates energy across the electromagnetic spectrum, from radio waves to visible light to powerful bursts of X-rays. By measuring the brightness, motion, and spread of this radiation, astronomers can infer how massive the central object must be to produce such effects. This method is indirect, but it is not guesswork. The physics of motion and gravity are well understood. If gas is orbiting at a certain speed, there is only so much mass that can be responsible for holding it there. If stars near a galactic center follow tight, fast orbits, the mass required to produce those motions can be calculated with precision. Over decades of observation, these techniques have been tested, refined, and cross-checked. As a result, black holes are now among the best constrained invisible objects in the universe. Their presence is inferred not from speculation, but from consistent, repeatable measurements that align with known physical laws. One of the most important discoveries of the last half-century is that black holes are not rare. In particular, supermassive black holes appear to be a normal feature of large galaxies. The Milky Way has one at its center. So do most spiral galaxies. So do giant elliptical galaxies. Wherever there is a substantial collection of stars bound together over billions of years, there is usually a massive black hole anchoring the system. These supermassive black holes are not leftovers from single collapsing stars. They are far too large for that. Instead, they grow gradually over cosmic time, accumulating mass through the slow infall of gas, dust and stars, and occasionally through mergers with other black holes when galaxies collide. Their masses typically range from millions to billions of times the mass of the Sun. Despite their reputation, most of the time these objects are quiet. They sit at the centres of galaxies without dramatic activity. Stars orbit peacefully at safe distances. Entire civilizations could exist in such galaxies without ever noticing the central black hole directly. Its influence is subtle, spread across vast scales, shaping the galaxy as a whole rather than disrupting individual systems. What makes supermassive black holes especially useful to astronomers is not their drama, but their consistency. They obey relationships. The mass of a supermassive black hole tends to correlate with the mass of the galaxy's central bulge. The speed of stars near the centre often reflects the black hole's influence. Over time, these patterns allow astronomers to estimate masses even when direct orbital measurements are difficult. All of this means that black holes are no longer theoretical curiosities. They are not speculative endpoints of equations. They are measurable objects with known properties, embedded in the architecture of the universe. Their masses can be estimated, their growth can be modelled, their effects can be observed across immense distances, and this is where comparison becomes essential. Once black holes are understood as physical entities, once their masses can be measured and placed on the same scale, differences begin to matter. A black hole that is twice as massive as another is not simply a little heavier. It bends spacetime more strongly. It influences matter farther out. It represents a different gravitational environment altogether. As astronomers began compiling catalogues of supermassive black holes, a sense of proportion emerged. Most fell within expected ranges. A few stood out as unusually large, but the majority clustered together, forming a landscape that felt, if not intuitive, at least familiar. That familiarity is what makes the exceptions meaningful. When one object appears whose mass lies far outside the established pattern, it is not treated as a curiosity. It becomes a question. Not a question of whether the object exists, but a question of how such mass accumulated and what conditions allowed it to grow so far beyond the norm. Understanding why mass comparisons matter requires understanding that gravity does not scale gently. Doubling mass does not simply double influence in a straightforward way. At extreme scales, small increases in mass can reorganize entire regions of space. They can change how galaxies evolve, how matter flows, and how energy is distributed across cosmic distances. This is why astronomers pay such close attention to the upper end of black hole mass. Not because larger is inherently more interesting, but because the extremes reveal where models hold and where they begin to strain. They show how far known processes can go before explanation requires refinement. Black holes, then, are not defined by mystery. They are defined by evidence. Their intrigue does not come from what is unknown, but from how much is known, and how far that knowledge can be pushed before intuition runs out. And once mass becomes the focus, once black holes are understood as measurable anchors of gravity rather than abstract voids, it becomes possible to recognize when one of them is no longer merely large, but genuinely set apart. Once black holes are understood as physical objects whose defining feature is mass, a natural question follows. How massive do they usually become? In nearby galaxies where measurements are most precise, supermassive black holes occupy a surprisingly narrow range. Narrow, at least by cosmic standards. Most fall between a few million and a few billion times the mass of the Sun. Within that span there is variety, but also consistency. These are not random values scattered without pattern. They reflect long periods of growth shaped by the structure and history of their host galaxies. One of the most familiar examples sits at the centre of the Milky Way itself. Sagittarius, a star, the supermassive black hole anchoring our galaxy, has a mass of a little over 4 million suns. That number may sound immense, and it is. Compressing 4 million suns into a region smaller than the orbit of Mercury is no small thing. Yet, in the broader context of supermassive black holes, Sagittarius A star is considered modest. Its importance lies not in its size, but in how well it can be studied. Because it is close, astronomers can track individual stars as they orbit the galactic centre. Some of these stars complete their paths in just a few decades, moving at astonishing speeds. By carefully measuring those orbits, scientists can calculate the mass required to keep them bound. The result is not speculative. It is precise, confirmed repeatedly, and refined over time. Sagittarius A star provides a clear reference point. It shows what a relatively quiet, nearby supermassive black hole looks like. It also demonstrates how tightly mass, motion, and gravity are linked. 4 million solar masses produce a specific gravitational environment, one that shapes the inner region of the Milky Way without overwhelming it. Beyond our galaxy, similar black holes appear again and again. In the Andromeda galaxy, the central black hole weighs in at around 100 million solar masses. In other nearby galaxies, values climb into the hundreds of millions and sometimes into the low billions. These are considered large examples, often hosted by massive galaxies with dense central bulges. Even at these scales, patterns persist. Astronomers have found that the mass of a supermassive black hole tends to correlate with the mass and motion of stars in the central region of its galaxy. This relationship suggests that black holes and galaxies grow together, influencing each other over billions of years. The black hole does not simply sit at the centre as an afterthought. Its growth is woven into the history of the galaxy itself. Because of this connection, most nearby supermassive black holes feel familiar once enough of them are studied. Their masses differ, sometimes by orders of magnitude, but they rarely feel unbounded. A black hole weighing a few billion suns is impressive, but not shocking. It fits within expectations shaped by decades of observation and theory. Some of the most massive, well-studied black holes in nearby galaxies approach 10 billion solar masses. These are typically found in giant elliptical galaxies formed through repeated mergers. Their growth histories are complex, marked by collisions, accretion, and long periods of quiet accumulation. Even so, they tend to settle into a range that feels like an upper shelf rather than an open sky. This is an important point. When astronomers talk about large supermassive black holes, they are not speaking loosely. They have reference points. They know what 4 million looks like. They know what 100 million looks like. They know what 1 billion looks like. By the time values reach several billion solar masses, attention increases, but disbelief does not. These numbers form a baseline. A sense of scale develops. Within it, differences matter, but they are differences of degree rather than kind. And then, occasionally an object appears that sits well outside this landscape. At first, such an object may not seem extraordinary. It might be bright, or distant, or unusually active. Its true significance often emerges slowly, as mass estimates are refined and compared. What makes it stand out is not that it exceeds expectations by a small margin, but that it does so decisively. This is where the idea of an outlier becomes meaningful. In statistics, an outlier is not just a large value, it is a value that resists explanation within the existing distribution. In astrophysics, the concept is similar. A black hole that is slightly heavier than its peers is interesting. A black hole that outweighs them by many times demands closer attention. The existence of outliers does not undermine the broader picture. On the contrary, it sharpens it. Extreme examples reveal the boundaries of known processes. They show how far accretion and mergers can be pushed. They expose where assumptions may need adjustment. Still, even extreme outliers are approached cautiously. Astronomers are well aware of the limitations of measurement, especially as distance increases. Nearby black holes benefit from detailed observations of individual stars and gas clouds. Distant ones do not. Their masses must be inferred through indirect methods, using light that has travelled for billions of years and carries only partial information about its source. This is why the baseline established by nearby galaxies is so important. It provides a stable reference against which distant measurements can be compared. When a distant black hole appears to exceed the mass of every nearby example by a wide margin, the claim does not stand alone. It rests on decades of accumulated understanding. It is also why caution remains. Larger black holes may exist unobserved, either because they are inactive or because their light does not reach us clearly. The universe is vast and surveys are incomplete. When astronomers speak of the largest known black holes, they're careful to emphasize what is known, not what is possible. And yet, knowledge still accumulates. As measurements extend farther into space and deeper into time, the familiar mass range of nearby supermassive black holes becomes a quiet anchor. It allows astronomers to recognize when a distant object is not merely large but exceptional, when its estimated mass does not simply exceed the norm but stands apart from it. Understanding this baseline is essential. Without it, large numbers lose context. With it, scale becomes meaningful. 4 million solar masses means something. 1 billion means something different. 10 billion marks an upper edge. And when a mass estimate rises far beyond even that, it becomes clear that comparison itself is about to change. When black holes are nearby, mass can be measured by watching individual stars move. Their paths curve, speed up, and repeat in ways that can be tracked over time. Distance makes that luxury disappear. For black holes far beyond the local universe, especially those seen as quasars, the stars around them cannot be resolved individually. The light arrives blended, stretched, and ancient. And yet mass can still be estimated with surprising reliability. This is where astronomy becomes an exercise in careful inference rather than direct inspection. Quasars are among the brightest persistent objects in the universe. They shine not because the black hole itself emits light, but because matter falling toward it releases enormous amounts of energy. Gas spirals inward, forming a rapidly rotating accretion disk. Friction, compression, and magnetic effects heat this material to extreme temperatures, causing it to radiate intensely across many wavelengths. That brightness is not noise, it is information. The first clue comes from motion. Gas in an accretion disk does not drift casually. It moves at tremendous speeds, orbiting closer and closer to the black hole as it loses energy. The faster the gas moves, the stronger the gravitational pull required to keep it bound. By measuring those speeds, astronomers can estimate the mass of the central object responsible. This motion reveals itself through spectral lines. When light from hot gas is spread into its component colors, specific fingerprints appear, produced by elements such as hydrogen, carbon, and magnesium. If the gas is moving rapidly, those lines broaden. The faster the motion, the wider the lines become. This widening is not subtle. It is measurable, repeatable, and directly tied to velocity. The relationship is straightforward in principle. Faster orbiting material requires a more massive central object. The details are complex, but the foundation is well understood. The same physics that governs planets, orbiting stars applies here, extended into a far more extreme regime. Brightness adds another layer. The total luminosity of a quasar is linked to how much matter is falling inward and how efficiently energy is being released. There is a theoretical upper limit to how bright an accreting black hole can become before radiation pressure begins to push incoming material away. This balance, first described by astrophysicists in the early 20th century, provides a useful reference point. When brightness and motion are considered together, they allow astronomers to estimate mass even when the black hole itself remains invisible. This approach is often referred to as reverberation mapping or virial mass estimation, depending on the details of the measurement. These methods are indirect, but they are not arbitrary. They're grounded in physical relationships that have been tested repeatedly in closer systems. Reliability comes from calibration. Nearby active galaxies where both stellar motion and gas behavior can be observed act as benchmarks. Astronomers compare the mass estimates derived from quasar techniques with masses measured through stellar orbits in these closer systems. Over time, the methods have been refined so that distant measurements align closely with local ones, within known margins of uncertainty. Uncertainty is not brushed aside. It is calculated explicitly. Every mass estimate comes with a range. That range reflects limitations in resolution, assumptions about geometry, and variations in the behavior of accretion disks. Rather than pretending these limitations do not exist, astronomers quantify them. They report upper and lower bounds. They revise values as models improve. They cross-check results using different spectral lines and independent observations. This is why mass estimates for quasars are rarely presented as single, rigid numbers. They are given as best estimates within a defined interval. The width of that interval matters. A narrow range inspires confidence. A wide one signals caution. What is important is that even with these uncertainties, some conclusions remain unavoidable. If a quasar's emission lines are extraordinarily broad and its luminosity exceptionally high, the mass required to produce those effects cannot be small. Even the lowest reasonable estimate may still place the black hole far above typical values. In such cases, uncertainty does not erase significance, it frames it. Another strength of these methods lies in their consistency across large samples. Thousands of quasars have been studied using similar techniques. Patterns emerge. Most fall into expected mass ranges. A few push toward the upper edge. Very few stand far beyond it. This statistical context matters. A single extreme value might raise suspicion. Repeated measurements showing similar results across independent studies carry more weight. When different teams, using different instruments and models, arrive at comparable conclusions, confidence grows. Institutions such as the European Southern Observatory and the Sloan Digital Sky Survey have played key roles in building this dataset. Large surveys provide uniform observations across vast regions of sky, reducing bias and improving comparison. Over time, the mass scale of quasars has become one of the most studied and refined areas of extragalactic astronomy. There is also a quiet elegance to these methods. They do not require exotic physics. They rely on gravity behaving as it always does, light carrying information faithfully across space, and motion leaving measurable signatures. The mystery lies not in how the measurements work, but in what they reveal. Still, caution remains central. Astronomers are careful to distinguish between precision and certainty. A precise measurement with large uncertainty is treated differently from one with a narrow range. Claims are adjusted as new data arrives. Values are revised, sometimes downward, sometimes upward. This process is not a weakness. It is the mechanism by which understanding improves. What matters most is that the uncertainty is known. When a black hole mass estimate includes a margin of error, that margin does not obscure the result. It defines its reliability. If even the lower bound of an estimate places the object among the most massive known, the conclusion remains strong. If the upper bound extends far beyond familiar ranges, the implication becomes harder to ignore. This is the position reached when studying the most extreme quasars. Their masses are not guessed. They are inferred through multiple overlapping lines of evidence. Each carries uncertainty, but together they converge. And so, when astronomers encounter a quasar whose inferred mass exceeds the known population by a wide margin, they do not rush to declare a record. They examine the assumptions, they test alternative explanations, they compare with other systems. Only when the numbers remain stubbornly large does the conclusion settle. Indirect does not mean unreliable, it means careful. These methods do not tell us everything. They do not reveal the exact structure of the accretion disk or the detailed history of growth, but they do provide a solid foundation. They allow astronomers to place distant black holes on the same mass scale as nearby ones, even when separated by billions of light years. And once that scale is established, it becomes possible to recognize when a measurement is not merely high, but exceptional. When uncertainty is acknowledged, quantified, and still unable to bring the value back into familiar territory, that is the threshold at which an extreme object stops being a curiosity and becomes something that quietly reshapes the landscape of comparison. There are objects in the universe that shine briefly, flaring into existence and then fading away. Supernovae do this. Gamma ray bursts do this. They appear suddenly, release enormous energy, and then vanish, leaving only remnants behind. Quasars are different. They are not fleeting events. They are persistent, sustained sources of light, visible across vast stretches of space and time. A quasar is not a star, nor a galaxy, nor a single explosion. It is a phenomenon created when a supermassive black hole is actively feeding. As matter falls inward, it does not plunge straight down. It spirals. Gas, dust, and debris form a rapidly rotating disk around the black hole, heating to extreme temperatures as friction and compression do their work. The energy released in this process is immense. In fact, it is among the most efficient energy-generating mechanisms known in the universe. Because of this, quasars can outshine entire galaxies. From enormous distances, a quasar can appear brighter than the combined light of hundreds of billions of stars. This is not because the black hole itself is luminous, but because the environment around it has become a powerful engine for converting mass into radiation. The process is steady, long-lived, and governed by well-understood physics. As long as matter continues to fall inward, the quasar continues to shine. This persistence is what makes quasars so valuable to astronomers. They act like beacons, visible across billions of light years. Light from distant quasars has travelled for much of the age of the universe before reaching Earth. When astronomers observe them, they are not seeing these objects as they are now, but as they were when the universe was far younger. In this way, quasars function as windows into deep cosmic time. Because the universe expands, light from very distant objects is stretched as it travels. Its wavelength increases, shifting toward the red end of the spectrum. This effect, known as redshift, allows astronomers to estimate how far away a quasar is, and therefore how long its light has been travelling. High redshift quasars are seen as they existed when the universe was only a fraction of its current age. This makes quasars more than just bright curiosities. They are probes of the early universe. Their light passes through intergalactic gas, revealing information about the conditions of space along the way. Their existence reveals how quickly massive structures formed after the first galaxies began to assemble. Their brightness allows them to be studied even when everything else at similar distances is too faint to detect. Crucially, quasars are also unmistakable indicators of active supermassive black holes. There is no known mechanism other than accretion onto a massive black hole that can sustain such enormous luminosity over such long periods. When a quasar is observed, astronomers can be confident that a black hole of extraordinary mass lies at its centre. Not every supermassive black hole produces a quasar. Most are quiet. They have little material falling inward and emit very little radiation. Quasars represent a phase, not a permanent state. A galaxy may host a quasar for millions or tens of millions of years and then settle into relative calm. During that active phase, however, the black hole grows rapidly, gaining mass while reshaping its environment. This growth phase leaves traces that can be measured long after the activity subsides. But while it is ongoing, it produces some of the clearest observational signals available to astronomy. Among the thousands of quasars catalogued over the decades, most fall within expected ranges of brightness and inferred mass. Some are more luminous than others, some lie farther away. Some exhibit particularly energetic outflows or distinctive spectral features. Over time, astronomers have built a detailed picture of what a typical quasar looks like, how it behaves, and what it implies about the black hole at its core. And then there are a few that resist easy placement. One such quasar was first identified not because it was dramatic or unusual in appearance, but because it was exceptionally bright at a very large distance. Its light showed signatures of extreme motion and energy output, suggesting a central engine of uncommon power. As observations accumulated, it became clear that this was not simply a bright quasar among many. It was an outlier. The quasar associated with TON 618 stands at a redshift indicating that its light began its journey billions of years ago, from an era when the universe was still relatively young. At that time, galaxies were still forming, merging, and evolving rapidly. The existence of a powerful quasar at such a distance already suggests a massive black hole. What drew attention, however, was just how massive the central black hole appeared to be. The brightness of the quasar, combined with the width of its emission lines, implied gas moving at extraordinary speeds under intense gravitational influence. Multiple studies, using different methods and data sets, converged on the same conclusion. The black hole powering this quasar was not merely large, it was extraordinarily so. This is what makes the quasar associated with TON 618 important. It is not a theoretical construct or a speculative object inferred from indirect clues alone. It is an observable phenomenon, studied through real light, captured by real instruments, analysed by independent teams over time. Its properties are measured, revised, and compared using the same frameworks applied to thousands of other quasars. What sets it apart is not mystery in the sense of ignorance, it is mystery in the sense of scale. The quasar shines with such intensity that it cannot be powered by a modest black hole. The observed motion of gas cannot be explained by familiar mass ranges. Even allowing for uncertainty, even applying conservative assumptions, the numbers remain stubbornly high. The central engine required to produce these observations lies far beyond the typical population. Importantly, this conclusion does not depend on a single observation or a single technique. It emerges from the combination of luminosity, spectral analysis, and distance. Each line of evidence reinforces the others. The quasar behaves exactly as expected for an object driven by an extremely massive black hole. In this way, the quasar serves as a bridge between observation and inference. It allows astronomers to move from light on a detector to a mass estimate grounded in physical law. It transforms something distant and abstract into something measurable and comparable. The quasar is not the black hole itself, but it is the black hole made visible. It is the consequence of gravity acting on matter at an extreme scale. Through it, astronomers gain access to an object that would otherwise remain entirely dark. By understanding the quasar first, its brightness, its distance, its behavior, it becomes possible to understand the black hole behind it not as a speculative giant, but as a physical entity whose properties can be constrained and compared, And once that connection is made, attention naturally shifts from the light to the source, from the quasar's glow to the mass required to sustain it, from the observable phenomenon to the object quietly shaping it from within. The object at the centre of this story is known as TON 618. It does not have a poetic name. It was not discovered because it looked unusual or dramatic. Its designation comes from an astronomical catalogue, a practical label assigned long before its true scale was understood. At first it was simply another distant quasar, one among many points of light scattered across the sky. What sets TON 618 apart is not how it appears but what it implies. TON 618 is associated with an exceptionally luminous quasar located at a vast cosmological distance. The light observed from this quasar began its journey billions of years ago, when the universe was far younger than it is today. By the time that light reaches Earth, it has been stretched by cosmic expansion, altered by intervening matter, and thinned by distance. And yet, even after all of that, it remains extraordinarily bright. Brightness at that distance is not a trivial detail. It immediately narrows the range of possible explanations. Sustained luminosity on this scale cannot be produced by stars, no matter how numerous. It cannot be maintained by short-lived explosions. It requires a long-term energy source of extreme efficiency. That source is accretion onto a supermassive black hole. When astronomers analysed the quasar associated with TON 618, they measured not only its brightness, but the motion of gas within it. The emission lines in its spectrum were unusually broad, indicating material moving at remarkable speeds. Those speeds, combined with the observed luminosity, pointed to a central object of extraordinary mass. Multiple studies, using independent datasets and methods, converged on a similar conclusion. The black hole powering this quasar was not merely larger than average, it was operating on a different scale entirely. The current best estimate for the mass of the black hole associated with TON 618 is approximately 66 billion times the mass of the Sun. That number is difficult to absorb without context, so context matters. Most supermassive black holes found in nearby galaxies weigh somewhere between a few million and a few billion solar masses. Sagittarius A star, at the centre of the Milky Way, weighs a little over 4 million suns. Many large elliptical galaxies host black holes in the range of 1 billion to 5 billion solar masses. Even the heaviest well-studied examples in the local universe tend to cluster below 10 billion. Against that backdrop, 66 billion stands apart. This is not a subtle difference. It is not a matter of rounding or revision. It is not a case where uncertainty could reasonably bring the value back into familiar territory. Even the most conservative lower bounds of the mass estimate place TON 618 well above every other known black hole. To put it another way, even if the mass estimate were revised downward significantly, the object would still remain the most massive black hole ever discovered. This is why astronomers are careful with the language they use here. The claim is not that TON 618 is the largest black hole that could exist. It is not that it represents some ultimate limit. The claim is narrower and stronger for it. Based on current observations and measurements, TON 618 is the most massive black hole known. That distinction matters. The mass estimate does not rely on a single measurement or a single assumption. It is supported by the quasar's luminosity, by the velocities inferred from spectral lines, and by models that have been calibrated against closer systems. Each method carries uncertainty, but they all point in the same direction. The black hole must be extraordinarily massive to produce what is observed. This consistency is what gives the estimate its weight. Astronomers are accustomed to extreme values that later soften with better data. In this case, the numbers have remained persistently high across revisions. The uncertainty has narrowed. The conclusion has not. What is also striking is how quietly this object exists. TON 618 is not violent in the way black holes are often imagined. It is not tearing apart nearby galaxies or flinging stars outward. It is distant, steady, and almost indifferent. Its influence is expressed through light that has travelled across most of cosmic history, carrying information rather than spectacle. There is a subtle irony here. The largest black hole ever discovered does not announce itself through destruction. It announces itself through brightness, through the steady conversion of matter into radiation, through processes that are well understood and repeatable. Its extremeness lies not in behaviour, but in scale. When scientists speak about objects like TON 618, they often return to comparison, because comparison is the only way scale becomes meaningful. A difference of a few million solar masses is interesting. A difference of tens of billions changes the landscape entirely. At 66 billion solar masses, the black hole associated with TON 618 outweighs Sagittarius, a star, by more than 15,000 times. It outweighs many large galaxy bulges. It sits far beyond the upper end of what was once considered typical, even for giant elliptical galaxies formed through repeated mergers. And yet it obeys the same physical laws as every other black hole. Gravity behaves as expected. Accretion follows familiar patterns. Light carries information, admits interpretation. Nothing about TON 618 requires new physics to exist. What it requires is a willingness to accept that known processes can operate at scales far larger than intuition would suggest. This is part of what makes the object scientifically valuable. It does not force a rewrite of theory, but it tests theory under extreme conditions. It asks whether existing models of growth, accretion, and cosmic evolution can accommodate such an outcome without breaking. So far, the answer appears to be yes. Barely. Growth through accretion and mergers can, in principle, build a black hole of this size. But the timeline must be efficient. The environment must be favourable. Long periods of uninterrupted feeding must occur early in cosmic history. These conditions are not impossible, but they are demanding. That is why TON 618 is not just large. It is informative. It marks the upper edge of what has been observed. It defines a reference point for what supermassive black holes can become. It shows how far-known mechanisms can be pushed before explanation begins to strain. Importantly, this status is not permanent. Astronomy does not grant eternal records. A more massive black hole may be discovered in the future, perhaps one that is quieter, darker, or farther away. TON 618 holds its place only for as long as observations allow. For now, however, it remains unmatched. Among all the black holes whose masses have been measured with reasonable confidence, TON 618 stands alone at the top of the scale. Not because it was sought out, but because evidence led there. Not because it behaves differently, but because it outweighs everything else by a wide margin. With that mass established, the question naturally shifts. Numbers describe weight, but weight has consequences. Gravity does not remain abstract at 66 billion solar masses. It reshapes space, time, and motion in ways that are difficult to ignore. And that leads directly to the next step. Understanding what such an extraordinary mass actually does to the universe around it. Once a number like 66 billion solar masses is stated, it can feel complete in itself, precise, impressive, and yet, without translating that mass into physical consequence, the number remains abstract. To understand what TON 618 truly represents, it helps to move away from catalogues and comparisons, and toward what that mass actually does to space-time. Gravity is not a force that reaches outward from an object like a hand pulling on a rope. In modern physics, gravity is the curvature of space-time itself. Mass tells space-time how to curve, and curved space-time tells matter and light how to move. At ordinary scales, this curvature is gentle. Planets orbit stars. Stars orbit galactic centers. Paths bend slightly, predictably. At extreme mass, the curvature deepens. A black hole does not create a special kind of gravity. It simply compresses mass into such a small region that the curvature becomes steep enough to trap everything that enters beyond a certain boundary. That boundary, the event horizon, marks the point where all possible paths through space-time lead inward. Once crossed, return is no longer possible. The size of that boundary depends entirely on mass. For a black hole like Sagittarius, a star, with a mass of just over 4 million suns, the event horizon would span a region roughly comparable to the orbit of Mercury. Large, but still contained within the inner reaches of a planetary system. For TON 618, the situation is very different. At approximately 66 billion solar masses, the Schwarzschild radius of TON 618 would extend to distances comparable to the size of the solar system. Not just the inner planets, but out toward the outer regions where gas giants reside. This does not mean that the black hole is a vast solid object filling that space. The event horizon is not a surface you could land on. It is simply the scale at which space-time becomes so steeply curved that escape is no longer possible. What is striking is not that such a radius exists, but how calmly it fits within known physics. The relationship between mass and Schwarzschild radius is linear. Double the mass, double the radius. There's no sudden transition, no threshold where gravity changes its nature. TON 618 follows the same rule as every other black hole, extended far beyond familiar territory. Outside the event horizon, space-time remains navigable. Objects can orbit. Light can escape. From a distance, the gravitational influence of a black hole is indistinguishable from that of any other object with the same mass. This means that TON 618 does not pull distant matter inward more aggressively than a star cluster or galaxy of equal mass would. Its influence is vast but not violent. The difference lies in how deeply space-time is curved near the centre. Close to TON 618, the geometry of space and time becomes extreme. Orbits tighten, velocities increase, time slows relative to distant observers. Light follows sharply bent paths. These effects are not speculative. They are predicted by general relativity and observed near smaller black holes. At this scale, they simply extend over a much larger region. One consequence of such mass is reach. The gravitational influence of TON 618 extends far beyond its event horizon, shaping the motion of gas and stars across enormous distances. Material does not need to be near the boundary to feel its presence. Even far out, the black hole acts as a central anchor, organizing motion and guiding the flow of matter inward over long periods. This is why accretion disks around supermassive black holes can span vast regions. Gas begins its slow inward journey from far away, gradually losing energy and angular momentum as it spirals inward. By the time it reaches the innermost regions, its speed and temperature have increased dramatically, releasing the energy that makes quasars shine. Importantly, the immense mass of TON 618 does not make this process chaotic. In fact, larger black holes often produce calmer local environments near the event horizon than smaller ones, because the curvature changes more gradually over distance. Tidal forces near the horizon can be weaker. A sufficiently massive black hole could, in principle, be crossed without immediate disruption, though what follows would still be final. This is one of those moments where intuition misleads. Larger does not always mean harsher at the boundary. It means more extensive. The region over which gravity dominates is larger. The scale of influence grows. But the physics remains consistent. From a cosmic perspective, this means that TON 618 is not a localized anomaly. Its mass contributes to the gravitational landscape of its host galaxy and beyond. It affects how gas settles, how stars move, and how energy flows through the surrounding environment. Over billions of years, these effects accumulate, shaping structure on scales that are difficult to visualize. Yet even here, restraint is important. TON 618 does not distort spacetime across the universe. Its influence, though vast, is still finite. Gravity weakens with distance. Beyond its immediate region, other masses dominate. Galaxies interact. Clusters form. The universe remains governed by the collective effect of countless objects. What makes TON 618 special is not dominance, but depth. The curvature of spacetime near it represents one of the deepest gravitational wells ever measured. To fall toward it is not to be pulled by a force, but to follow a path through spacetime that grows increasingly steep. Escape becomes harder not because something grabs you, but because all available directions lead inward. This distinction matters, because it keeps the discussion grounded in physics rather than imagery. Black holes are not cosmic vacuum cleaners. They do not roam the universe consuming everything nearby. They sit. They curve space-time, and matter responds according to well-defined rules. At 66 billion solar masses, those rules produce effects on a scale that stretches comprehension. But they do not break. This translation from mass to consequence is essential. Without it, TON 618 remains a number. With it, the object becomes something that can be placed within the structure of space-time itself. Its size is no longer just a comparison to other black holes, but a statement about how space and time behave in its presence. And once those physical consequences are clear, a deeper question begins to emerge. If gravity behaves this way at such mass, if space-time can be curved so extensively by a single object, how did it get there in the first place? Mass does not appear spontaneously. It accumulates. It grows. It requires time, material, and conditions that allow gravity to work uninterrupted. Understanding what 66 billion solar masses means for spacetime naturally leads to curiosity about the path that led to such an outcome. That path is not written into the fabric of space itself. It is written into cosmic history. A black hole with a mass of 66 billion suns invites a simple question that turns out not to be simple at all. How does something like that grow? Black holes are not born large. Even the most massive ones begin from comparatively modest beginnings. Growth is gradual, governed by processes that operate over immense spans of time. There are two primary ways a black hole increases its mass: accretion and mergers. Both are well understood in principle. Both are observed throughout the universe, and both are essential to explaining how supermassive black holes come to exist. Accretion is the slower, steadier process. Matter falls inward from the surrounding environment, drawn by gravity. Gas clouds drift closer, stars wander too near, dust settles into orbit. As this material spirals inward, it forms an accretion disk, heating up and releasing energy, before finally crossing the event horizon. Once it does, the mass is added permanently. Nothing escapes. Growth is cumulative. This process is remarkably efficient. Converting matter into energy through accretion releases far more energy per unit mass than nuclear fusion inside stars. That efficiency is what powers quasars and active galactic nuclei. It is also what allows black holes to gain mass steadily over long periods, provided there is enough material available. But accretion has limits. As matter falls inward and heats up, it produces radiation. That radiation pushes outward. If the outward pressure becomes too strong, it can slow or even halt further infall. This creates a natural balance point. Black holes can grow rapidly, but not arbitrarily fast. there's a maximum rate at which mass can be added, while still allowing matter to fall inward efficiently. Over millions or billions of years, however, even a steady rate adds up. A black hole that accretes continuously, without interruption, can grow dramatically. Given enough time and enough fuel, accretion alone can build objects of enormous mass. The second growth mechanism is more abrupt. Mergers occur when galaxies collide, and their central black holes eventually find each other. These events are rare on human timescales, but common over cosmic history. Galaxies merge frequently, especially in the early universe. When they do, their black holes begin a slow gravitational dance, spiraling inward until they combine into a single, more massive object. Mergers add mass in large steps rather than gradual increments. Two black holes become one. Some mass is radiated away as gravitational waves, but most is retained. Over time, repeated mergers can significantly boost mass, especially in dense regions where galaxies cluster and interact. Together, accretion and mergers form the backbone of black hole growth models. They explain why supermassive black holes tend to be found at the centers of large galaxies. They account for observed correlations between black hole mass and galactic structure. They provide a framework that matches the majority of observations remarkably well. And for most black holes, this framework is sufficient. But TON 618 sits at the far edge of what these processes comfortably explain. In principle, there's nothing forbidden about building a black hole of 66 billion solar masses. Accretion and mergers can do it. The challenge lies not in possibility, but in timing. The universe has a finite age. Light from TON 618 left its source billions of years ago, meaning the black hole had already reached an extraordinary mass relatively early in cosmic history. This compresses the available timeline. To grow that large, a black hole must either accrete matter at near its maximum rate for long periods, experience multiple major mergers, or begin from an unusually massive starting point. Each of these scenarios is plausible. All of them together begin to strain simplicity. For example, continuous accretion requires a stable supply of gas over immense spans of time. The gas must not be blown away by radiation or disrupted by galactic dynamics. Major mergers require the right environments, with frequent galaxy collisions and enough time for black holes to sink toward the center and merge. Massive initial seeds suggest early formation pathways that bypass smaller stages altogether. None of these ideas are speculative in isolation. Astronomers observe accretion. They observe mergers. They study early universe conditions that could allow massive seeds to form. What makes TON 618 scientifically important is that it pushes all of these mechanisms toward their upper limits simultaneously. This is where language matters. Growth models are challenged, not broken. The existence of TON 618 does not contradict known physics. It does not demand new forces or exotic processes. Instead, it forces existing models to operate at their most extreme, most efficient settings. It asks whether the universe, under the right conditions, can assemble such mass quickly enough using familiar tools. So far the answer appears to be yes, but only just. This tension is productive. It sharpens questions rather than dissolving them. It motivates closer study of early galaxy formation, gas dynamics, and the behavior of black holes in dense environments. It encourages astronomers to examine whether the earliest black holes formed from collapsing stars, dense star clusters, or direct collapse of massive gas clouds. TON 618 does not sit outside theory, it sits at the edge of it. There is also a subtle shift in perspective here. For smaller black holes, growth history often feels like a detail. For an object of this scale, growth history becomes central. The mass itself is not the most interesting feature. The path that led there is. Every additional billion solar masses represents time, material, and opportunity. It represents a period when the black hole was actively feeding, or a moment when galaxies merged. Stacked together, those moments form a narrative written across billions of years. That narrative is not fully resolved. It does not need to be. Science rarely delivers complete stories all at once. What matters is that the pieces fit together without contradiction, even if some details remain blurred. TON 618 shows that black hole growth can be extraordinarily effective under the right conditions. It demonstrates that the universe is capable of assembling immense concentrations of mass without breaking its own rules. It also highlights where understanding becomes delicate, where assumptions must be tested carefully rather than taken for granted. This is why TON 618 matters beyond its size. It acts as a stress test for models of cosmic evolution. It reveals what is possible when gravity, time, and environment align in particular ways. It reminds astronomers that averages describe most objects, but extremes reveal the full range of behavior. And once growth mechanisms are stretched to their limits, attention naturally turns backward in time, to the conditions that existed when the universe was younger, denser, and more chaotic, to the era when the seeds of the larger structures were planted. If a black hole could grow this massive this early, then the environment that allowed it must have been unusual as well. Understanding that environment requires stepping deeper into the early universe, where galaxies were still forming and the rules of structure were being written for the first time. That is where the story continues. When the light from the quasar associated with TON 618 began its journey, the universe was very different from the one seen today. Galaxies were younger, denser, and still settling into recognizable shapes. Large-scale structure was emerging, but much of the cosmic landscape was unfinished. The universe had not yet reached half its current age. That timing matters, because astronomy looks outward in space and backward in time simultaneously. Distance becomes a kind of clock. The farther away an object is, the earlier its light was emitted. In the case of TON 618, that light has travelled for billions of years before arriving at Earth, carrying information from an era when the universe was still in an active phase of formation. This means that the black hole powering that quasar had already reached an extraordinary mass at a relatively early point in cosmic history. To appreciate why this is striking, it helps to consider the pace of cosmic growth. After the universe began, matter needed time to cool, clump, and form the first stars. Those stars then lived and died, enriching their surroundings with heavier elements. Galaxies assembled gradually through mergers and accretion. Black holes formed and grew alongside these processes, not ahead of them. Everything took time, yet by the time the light from TON 618 was emitted, its central black hole had already grown to tens of billions of solar masses. This compresses the growth timeline significantly. The processes described earlier, accretion and mergers, must have operated efficiently and persistently over a shorter span than they usually do for black holes of comparable mass seen closer to the present day. This does not imply anything impossible. It does, however, narrow the range of viable histories. For a black hole to reach such mass early on, several conditions must align. There must be an abundant supply of gas. That gas must be able to fall inward without being blown away by radiation for extended periods. Mergers must occur frequently enough to add mass in large increments, and interruptions must be minimal. In the early universe, some of these conditions were more common than they are now. Galaxies were closer together, gas was more plentiful, collisions were more frequent, environments were chaotic, but also fertile. In that sense, early cosmic history offered opportunities that are rarer today. Even so, the scale of TON 618 remains demanding. This is why its timing continues to draw attention. Astronomers are not puzzled by its existence in the sense of confusion. They understand the mechanisms involved. What remains under study is how those mechanisms combined so effectively, so early and with such consistency. Research in this area is active and ongoing. Some studies focus on the nature of the initial black hole seeds. Rather than beginning as small remnants of stars, some early black holes may have formed from the direct collapse of massive gas clouds, bypassing intermediate stages entirely. Such seeds would start larger, reducing the amount of growth required later. Other work examines sustained periods of near maximum accretion. Under certain conditions, radiation pressure may not halt infall as quickly as once assumed, allowing black holes to feed more efficiently for longer spans. These scenarios are explored through simulations grounded in known physics, not speculation. There is also continued investigation into the merger history of early galaxies. If TON 618 formed in a particularly dense region, it may have experienced a sequence of mergers that accelerated its growth beyond typical expectations. Observations of galaxy clustering and structure formation support the idea that such regions existed. None of these avenues require new laws of nature. They refine how known processes are applied under early universe conditions. This is an important distinction. The mystery here is not ignorance of physics, but sensitivity to timing. The universe does not distribute opportunity evenly. Some regions experience faster growth than others. Some objects benefit from rare alignments of conditions. TON 618 appears to be an example of this, a product of circumstances that were unusual but not impossible. What makes this especially compelling is that timing can be tested. As more distant quasars are discovered and studied, astronomers can compare their inferred masses and ages. Patterns begin to emerge. Some black holes grew rapidly early on. Others followed slower, steadier paths. By assembling these comparisons, researchers build a clearer picture of how common extreme early growth really was. So far, objects like TON 618 remain rare. That rarity is informative. It suggests that while rapid early growth is possible, it requires specific conditions that do not arise everywhere. TON 618 is not representative of early black holes as a whole. It is an outlier, even among distant quasars. This is where timing becomes a source of intrigue rather than confusion. The universe allowed such growth, but did not repeat it often. That selective outcome tells a story about environment, availability, and chance, all operating within the boundaries of physical law. It also reminds astronomers to be cautious. Observing distant objects means working with limited information. Light from early epochs is faint, stretched, and filtered through intervening space. Measurements are more challenging. Uncertainties grow. Conclusions must be framed carefully. Still, even with these limitations, some statements remain robust. TON 618 was already massive when the universe was young. Its growth must have been efficient. Its environment must have been favourable. These facts persist across revisions and refinements. This makes timing one of the most valuable pieces of evidence in understanding the object. Mass tells us what exists. Timing tells us when it existed. Together, they constrain how it came to be. Importantly, researchers resist the temptation to fill gaps with speculation. Where models remain incomplete, they are labelled as such. Where multiple explanations fit the data, they're compared rather than ranked prematurely. The goal is not to force a narrative, but to let evidence guide interpretation. As new instruments come online and surveys extend deeper into space, the timeline of early black hole growth continues to sharpen. Each additional data point helps refine how unusual TON 618 truly is, and whether it represents a rare peak or the visible edge of a broader distribution. For now, its timing remains one of its most intriguing features, not because it defies understanding, but because it compresses known processes into a shorter window than usual. It shows how quickly gravity can work when conditions allow. And yet all of this insight rests on observation, on light that has travelled for billions of years, carrying partial information across an expanding universe. Understanding timing is inseparable from understanding the limits of what can be observed. As attention shifts from when TON 618 existed to how precisely it can be measured, the role of observational boundaries becomes impossible to ignore. Distance is not just a measure of how far away something is. In astronomy, distance is also a measure of how much information has been lost along the way. When astronomers observe nearby black holes, they work with light that has travelled for relatively short periods of time. The signal is strong, details are preserved, individual stars and gas clouds can sometimes be resolved. Motion can be tracked directly. In these cases, mass estimates can be refined repeatedly, narrowed down with confidence, and tested against multiple independent observations. As distance increases, that clarity fades. Light from distant objects arrives weakened, stretched, and filtered by the universe it has crossed. By the time it reaches Earth, it carries only a fraction of the information it once held. This does not make it useless, but it does require care in how conclusions are drawn. TON 618 exists at an immense distance. The light used to study it has travelled for billions of years, passing through expanding space and intervening matter. Along the way, its wavelength has been stretched, a process known as redshift. Redshift is not a distortion or an error. It is a predictable consequence of cosmic expansion, but it does change how information is encoded in the light. As wavelengths stretch, features in the spectrum shift position. Some move out of detectable ranges, others become harder to separate cleanly. The further away a source is, the more pronounced these effects become. This is why distant observations rely on fewer spectral lines and broader measurements rather than fine detail. Ancient light also represents a snapshot, not a continuous record. Astronomers see distant objects as they were, not as they evolved. Variations over time are averaged together. Short-lived fluctuations disappear. What remains is an integrated signal, carrying the dominant features but smoothing over nuance. These limitations are not ignored, they are built into the analysis. When astronomers estimate the mass of a distant black hole like TON 618, they account for the effects of redshift, signal strength, and resolution. Models are adjusted to reflect what can and cannot be known from the available data. Assumptions are stated explicitly. Uncertainty ranges are included alongside central values. This is where restraint becomes essential. The mass estimate of approximately 66 billion solar masses does not pretend to be exact to the last decimal. It is a best estimate within a defined range. That range reflects uncertainties in geometry, orientation, and the behaviour of gas near the black hole. It also reflects the limits imposed by distance. What is important is how those uncertainties behave. Even when conservative assumptions are applied, even when the lower bounds of the estimate are emphasized, TON 618 remains extraordinarily massive. The uncertainty does not collapse the mass into familiar territory. It shifts the number slightly up or down, but it does not change its position relative to other known black holes. This distinction matters. Some aspects of TON 618's mass are robust. The extreme brightness of the quasar is not in question. The broad emission lines indicating rapid gas motion are well measured. The distance derived from redshift is firmly established. These factors together place a strong lower limit on the black hole's mass. Other aspects are less certain. The exact structure of the accretion disk cannot be resolved. The precise orientation of the system relative to Earth introduces ambiguity. The distribution of gas may differ from simplified models. These uncertainties affect the final number, but within known bounds. This is why astronomers emphasize ranges rather than absolutes. A mass estimate is not a single claim. It is a statement about probability and consistency. It says that given the data available, and given what is known about physics, the black hole must fall within a certain interval. For Ton 618, that interval sits entirely above the mass of every other black hole measured so far. Distance also limits comparison. Nearby black holes benefit from direct measurement techniques that are simply unavailable at great distances. This creates an asymmetry in confidence. Local black holes can be weighed with extraordinary precision. Distant ones cannot. As a result, astronomers are careful not to overinterpret small differences among distant objects. But when differences become large, caution works differently. If two distant black holes differ by a small factor, uncertainty might erase the distinction. If they differ by an order of magnitude, uncertainty becomes less relevant. Ton 618 falls into the latter category. Its estimated mass is not marginally higher than others, it is dramatically higher. This does not mean the estimate is immune to revision. Science remains open to refinement. Improved observations, new instruments, and better models may adjust the number, but revision does not imply reversal. The object's position at the extreme upper end of the distribution is unlikely to change. This careful balance between confidence and humility defines modern astronomy. Researchers resist the urge to claim certainty where data does not allow it. At the same time, they do not retreat from conclusions that remain supported across reasonable assumptions. Distance forces this discipline. It reminds astronomers that observation is always partial, that the universe does not present itself cleanly or completely, that even the brightest objects at great distances arrive softened by time and space. And yet, within those constraints, patterns still emerge. Comparisons remain possible. Extremes can be identified. Ton 618 is one such extreme, not because its mass is known with perfect precision, but because its mass is known well enough to stand apart. This honesty about uncertainty strengthens the conclusion rather than weakening it. It shows that the claim is not built on wishful thinking or selective interpretation. It rests on careful analysis that acknowledges limitations without being paralyzed by them. As attention turns outward, another question naturally arises. If distance hides detail, could it also hide even larger black holes? Could there be objects more massive than Ton 618, quieter, darker, or simply farther away, waiting beyond the reach of current surveys? This is not a suggestion of missing knowledge. It is a recognition of scale. Understanding what is known requires understanding what cannot yet be seen, and that boundary between observation and absence is where the next layer of inquiry begins. When astronomers describe something as the largest known, the phrase carries more care than it might first suggest. It is not a declaration of finality. It is a statement about evidence. It reflects what has been observed, measured, and compared so far within the limits imposed by distance, technology, and time. Largest known does not mean largest imaginable. It does not mean largest possible. It means that among all objects whose properties have been measured with reasonable confidence, none exceed it. This distinction is essential, especially when discussing objects as extreme as supermassive black holes. Astronomy does not work with complete inventories. The universe is vast and observation is necessarily selective. Telescopes survey portions of the sky. Instruments operate within finite sensitivity. Some objects shine brightly and announce their presence. Others remain quiet, emitting little radiation and offering few clues. What is known is always a subset of what exists. When Ton 618 is described as the largest black hole ever discovered, the claim rests on comparison. Its mass has been estimated and placed alongside those of other supermassive black holes, measured using similar methods. Within that catalogue, it sits at the top by a wide margin. No other known object approaches its mass. That comparison is meaningful precisely because it is cautious. Astronomers avoid absolute language not out of hesitation, but out of accuracy. They recognize that absence of evidence is not evidence of absence. Larger black holes could exist beyond current detection limits. They might reside in regions of space that have not been surveyed deeply. They might be inactive, surrounded by little gas, producing no quasar and very little light. They might be so distant that their signals are too faint to interpret clearly. All of these possibilities are real. What matters is that such objects, if they exist, have not yet been measured in a way that allows confident comparison. Until they are, they remain hypothetical rather than known. This is why astronomers frame records carefully. TON 618 is the largest black hole measured so far. It holds that status because evidence places it there, not because theory demands it. The distinction between measured and possible is not a technicality. It reflects how science advances. Knowledge grows outward from what can be observed reliably. Each new instrument expands that boundary. Each new survey fills in gaps. Records shift not because previous claims were wrong, but because the sample grows. There is historical precedent for this. In the past, the largest known stars, galaxies, and clusters have all changed as observations improved. Early measurements were limited by resolution and sensitivity. As technology advanced, new extremes were revealed. Each discovery refined understanding rather than overturning it. Black holes are no different. For a long time, stellar mass black holes were thought to top out at relatively modest masses. Improved observations expanded that range. Supermassive black holes were once speculative. They are now well established. Each stage of discovery extended known limits without implying that the universe had reached an endpoint. TON 618 occupies the current frontier of that process. Its mass is not special because it approaches a theoretical ceiling. There is no known upper bound on black hole mass imposed by fundamental physics alone. Growth is constrained by environment and time, not by a hard limit written into gravity itself. Given sufficient material and opportunity, a black hole can, in principle, continue to grow. What limits growth in practice are conditions. Galaxies must supply gas, mergers must occur, accretion must proceed without prolonged interruption. These requirements become harder to satisfy as mass increases, but they do not forbid further growth. They simply make it rarer. This rarity is reflected in observation. Extremely massive black holes are uncommon. Most galaxies host black holes well within familiar ranges. A few reach the upper billions. Objects like TON 618 appear only occasionally at great distances under particular circumstances. That scarcity is part of what gives the phrase largest known its weight. It signals that the object is not just an incremental step beyond the average, but a clear outlier. At the same time, restraint prevents overstatement. Astronomers do not claim that TON 618 represents the maximum size a black hole can reach. They do not suggest that anything larger would violate physics. They simply state that nothing larger has yet been measured with confidence. This balance between confidence and humility is deliberate. It avoids false absolutism, the temptation to treat current knowledge as final. It leaves room for future discovery without diminishing the significance of what is already known. There's also an important psychological aspect to this framing. When extremes are presented as ultimate, they invite premature conclusions. When they are presented as provisional, they invite continued exploration. TON 618 benefits from this approach. Its importance does not depend on being the final record holder. It matters because it demonstrates what is achievable under real cosmic conditions. It shows how far black hole growth can be pushed without breaking known physics. Whether it remains the largest known for decades or is eventually surpassed does not change that lesson. In this sense, largest known is not a boast. It is a snapshot. It captures the current edge of observation, Frozen in time until new data arrives, it reflects both achievement and limitation. Achievement, because measuring such an object at such distance is remarkable. Limitation, because the universe almost certainly contains more than has been seen. This duality is a quiet theme running through astronomy. Every discovery expands knowledge, while simultaneously revealing how much remains unseen. Extremes sharpen that awareness. When speaking about TON 618 then, it is accurate to say that it is the most massive black hole discovered so far. It is equally accurate to acknowledge that larger ones may exist beyond current reach. Holding both ideas at once is not contradiction, it is honesty. This honesty allows attention to shift naturally away from records and toward meaning. Once absolutes are set aside, scale becomes less about competition and more about perspective. The question is no longer whether TON 618 is the biggest possible, but what its size tells us about the universe that produced it, about the environments that allow such growth, about the relationship between gravity, time and structure. By framing TON 618 as the largest known rather than the largest conceivable, astronomy keeps the focus where it belongs, on understanding, not finality, on process, not endpoints. And as that focus deepens, the conversation begins to move beyond measurement altogether. Numbers still matter, but they become gateways rather than destinations. Once the idea of absolute limits is released, what remains is scale itself, how the universe accommodates extremes, how human intuition responds to them, how meaning shifts when size exceeds familiar categories. That is where the discussion naturally begins to turn next. There is a point at which numbers stop behaving the way the human brain expects them to. Below that point, scale feels manageable. 10 is clearly more than 1. 1,000 feels comfortably larger than 100. Even 1,000,000, while abstract, can still be grasped as a big collection of smaller things. Beyond that, intuition begins to thin out. This is not a personal limitation. It is a biological one. Human perception evolved to deal with distances measured in steps, time measured in days, and quantities measured in handfuls or crowds. The brain is very good at comparing objects within a narrow range. It is far less comfortable when differences span many orders of magnitude. This becomes especially clear in astronomy. When hearing that a black hole weighs 4 million times the mass of the Sun, the number sounds large, but it can still be anchored to something familiar. The Sun is known. Millions are imaginable, at least conceptually. When the number rises to 1 billion, the sense of scale becomes more fragile, but comparison still functions. 1 billion is larger than 1 million by a clear factor. The difference matters. At tens of billions, something changes. 66 billion solar masses is not just bigger than 1 billion. It exists in a region where comparison itself begins to lose usefulness. The difference between 10 billion and 60 billion is mathematically clear, but cognitively hollow. Both are simply enormous. Neither maps cleanly onto experience. This is why descriptions of extreme objects often rely on metaphor and analogy, even when those tools are imperfect. Without them, numbers float without weight. With them, meaning can be approximated, though never fully captured. Cognitive scientists have long noted that the brain tends to compress large ranges into vague categories. Beyond a certain point, larger no longer feels meaningfully different from largest. This is why phrases like unimaginably large exist. They are not exaggerations, they are admissions. In the case of TON 618, this compression happens quickly. Once the mass reaches tens of billions of suns, the distinction between one such black hole and another becomes academic rather than intuitive. The mind no longer asks how much larger. It asks what that largeness signifies. This shift matters. At smaller scales, comparison is informative. A black hole twice as massive as another will have a noticeably stronger influence on its surroundings. Differences are tangible. At extreme scales, the influence becomes so dominant that further increases change the picture less dramatically than expected. Gravity is already overwhelming. Space-time is already deeply curved. Adding more mass extends these effects, but does not introduce entirely new categories of experience. This is why astronomers often speak carefully at the upper end of scale. Precision remains essential for calculation, but narrative meaning shifts. The question is no longer how much bigger, but what it implies about the universe's capacity to produce such extremes. There is also a subtle psychological effect at work. Extreme scale tends to erase reference points. When comparing everyday objects, the brain relies on contrast. A mountain is large because it towers over a person. A planet is large because it dwarfs a mountain. A star is large because it dwarfs a planet. Each step builds on the last. At some point, the ladder runs out. A black hole of 66 billion solar masses does not sit neatly on that ladder. It does not feel proportionally larger than one of 10 billion. Both are far beyond the last rung that experience provides. This is where language begins to struggle. Words like massive, enormous, and colossal lose resolution. They flatten. They become placeholders rather than descriptors. Even technical terms, when repeated often enough, begin to feel symbolic rather than informative. This is not a failure of language so much as a signal that abstraction has taken over. Physicists are accustomed to working in this space. They rely on mathematics to handle scale precisely, even when intuition fails. But for communication, especially outside equations, something else is needed. A slower pace, a willingness to sit with uncertainty, an acceptance that understanding does not always mean visualization. This is where quiet awe enters. Awe is not surprise or excitement. It is a recognition that something exists beyond comfortable comprehension, yet remains real and structured. It does not demand explanation in emotional terms. It allows facts to stand without forcing them into familiar shapes. TON 618 invites this kind of response. Its mass is not shocking because it is violent or chaotic. It is striking because it is calm. Gravity operates smoothly. Space-time curves predictably. Nothing about the object is unstable or erratic. It simply exists at a scale that does not fit easily into mental models. This calm extremity is often overlooked. Popular descriptions of black holes emphasize danger and drama. In reality, the most massive black holes are among the most orderly objects in the universe. Their behavior is governed by simple principles applied consistently. Their influence is steady. Their growth, though remarkable, follows understandable paths. Recognizing this can be grounding. It reframes scale not as something threatening, but as something indifferent. The universe does not exaggerate. It does not seek to impress. It allows extremes to arise because the rules permit them, not because they are special in a human sense. This indifference is part of what makes extreme scale difficult to process. Human meaning tends to attach importance to intention. When something is large without intent, powerful without purpose, the mind searches for narrative and finds none. What remains is structure. In that structure, abstraction becomes a tool rather than a barrier. Numbers are not meant to be felt emotionally. They are meant to be used. When they exceed intuition, the correct response is not to force understanding but to acknowledge its limits. This acknowledgement does not diminish knowledge. It refines it. By accepting that tens of billions of solar masses cannot be meaningfully imagined, attention shifts to what can be known. How gravity behaves, how space-time responds, how such mass could accumulate. These questions remain accessible even when visualization fails. This is why comparisons eventually give way to description. Not because comparison is wrong, but because it stops adding insight. saying that ton 618 is many times larger than another black hole communicates hierarchy but not consequence. To understand consequence, abstraction is required. Abstraction allows scale to be handled without distortion. It replaces mental pictures with relationships, with patterns, with constraints. It is less vivid, but more accurate. In this way, the struggle to comprehend extreme scale is not a flaw. It is a guide. It signals where language must slow down and precision must take over. It marks the boundary between experience and explanation. And that boundary is not something to rush past. It is a place to pause, to let the numbers remain what they are without forcing them into metaphor, to allow the universe to be larger than intuition without becoming inaccessible. From here, the conversation naturally shifts again, away from numbers and toward the tools used to carry them, toward language itself, toward how scientists describe what cannot be pictured, and how meaning survives even when imagery falls away. That transition does not reduce wonder. It deepens it quietly by allowing abstraction to speak in its own restrained voice. When objects move beyond the scale of everyday experience, science does not try to make them feel familiar. It does something quieter. It becomes more precise. Numbers are the primary tool for this precision. They are not there to impress or overwhelm. They exist to anchor understanding when intuition can no longer be trusted. In astronomy, numbers replace imagery not because imagery is discouraged, but because it eventually stops being useful. This shift happens naturally as scale increases. For nearby objects, description often begins with pictures. A star can be imagined as a glowing sphere. A planet can be imagined as a world. Even a galaxy can be pictured as a vast but recognizable structure. At these scales, visualization supports understanding. Ton 618 does not belong to this category. Its mass, its distance, and its influence exceed the range where pictures help. No mental image can accurately represent 66 billion solar masses compressed into a region defined by spacetime curvature. Any picture that tries will either exaggerate or simplify in misleading ways. This is why scientists lean so heavily on numbers when discussing objects like this. Numbers do not pretend to be intuitive. They are exact, even when they feel abstract. They allow relationships to be described without distortion. For example, stating that Ton 618 has a mass of approximately 66 billion times. The mass of the Sun immediately places it within a quantitative framework. That number can be compared to other black holes, inserted into equations of gravity, and used to predict physical effects. It does not need to be imagined to be meaningful. Metaphors often step in when numbers feel cold. They can be helpful at smaller scales. Comparing a black hole's event horizon to the size of a city or a planetary orbit can give a rough sense of extent. But for Ton 618, metaphors reach their limits quickly. Saying that its event horizon could span distances comparable to the solar system is informative but incomplete. It gives scale without consequence. It suggests size without conveying what that size does to space-time, motion, and time itself. More elaborate metaphors risk doing harm. They imply solidity where none exists. They suggest violence where there is order. They turn gravity into something that pulls rather than something that shapes. This is why metaphors are used sparingly in serious discussion of extreme objects. They are treated as temporary guides, not explanations. Scientists are comfortable letting numbers stand on their own. They understand that comprehension does not always require a mental picture. In many areas of physics, understanding comes from relationships rather than images. No one visualizes a magnetic field directly, yet its effects are well understood. No one pictures time dilation as an object, yet it can be measured and predicted precisely. Black holes at extreme mass belong in this category. Understanding Ton 618 does not require imagining what it looks like. It requires understanding how its mass influences space-time, how that influence affects surrounding matter, and how those effects are detected. These are relational concepts, not visual ones. This is a subtle but important reframing. Instead of asking what it looks like, the more useful question becomes what it does. How fast does gas move around it? How far does its gravitational influence extend? How does time behave near it relative to distant observers? How does light respond to its presence? Each of these questions can be answered with numbers, equations written in full English, and observed patterns. None require imagery. This approach may feel less satisfying at first, especially for audiences accustomed to dramatic visuals, but it's closer to how scientists themselves think. They work with constraints, not pictures, with ranges, not scenes, with relationships that remain valid even when intuition fails. There's also an honesty in this method. By avoiding over-reliance on metaphor, scientists acknowledge the limits of human perception. They do not pretend that everything can be brought down to a familiar scale. They accept that some aspects of the universe exist outside the range of comfortable imagination. This acceptance does not diminish understanding, it deepens it. TUN 618 is not less real because it cannot be visualized. It is more firmly grounded because its properties are defined numerically. Its mass is not a story. It is a measurement. Its influence is not imagined. It is calculated and observed. This is why numbers persist even when they feel unsatisfying. They survive where metaphors fail. At the same time, numbers are not the end of the story. They're a bridge back to physical reality. Once mass is specified, physical consequences follow. Space-time curvature can be described. Orbital velocities can be predicted. Accretion behavior can be modeled. These predictions can then be checked against observation. Agreement reinforces confidence. Disagreement signals the need for refinement. In this way, abstraction does not replace reality. It connects to it. This connection is especially important for extreme objects. Without it, scale becomes spectacle. With it, scale becomes structure. Scientists are careful not to confuse the two. TUN 618 is impressive, but not because it invites astonishment. It is impressive because it fits into known frameworks while stretching them. Its numbers are large, but they behave properly. Gravity does not misbehave. Time does not fracture. The universe accommodates this object without strain. This accommodation is itself informative. It tells us that space-time is flexible enough to host such mass, that the rules governing gravity are robust across an enormous range, that the same equations describe both the orbit of a planet and the behavior of a quasar powered by a black hole tens of billions of times the mass of the Sun. That continuity is one of the quiet achievements of physics. It also explains why visualization is optional. The universe does not require that its structures be imagined to function. It only requires that they obey relationships. Understanding those relationships is enough. For listeners, this can be freeing. There is no obligation to picture TUN 618 accurately. No mental image will capture it anyway. What matters is recognizing that it exists, that its mass has consequences, and that those consequences can be described and tested. This reframing shifts the role of language as well. Instead of trying to evoke images, language becomes a tool for precision. Words describe limits, ranges, and behaviors rather than scenes. Sentences slow down to avoid exaggeration. Meaning emerges through careful construction rather than emotional impact. In this mode, mystery does not come from the unknown, but from scale itself, from the recognition that something can be fully described in numbers and still remain beyond intuition. TUN 618 sits comfortably in that space. It is known, measured, and understood within the limits of current science. At the same time, it resists mental capture. That resistance is not a failure of explanation. It is a feature of the universe at extreme scale. By accepting that understanding does not require visualization, the conversation returns to what can be examined directly. How mass shapes spacetime, how gravity organizes matter, how light carries information across billions of years. From abstraction, attention naturally moves back toward physical consequence. Numbers open the door. What lies beyond is not imagery but behavior, and it is there, in the observable effects of extreme mass, that the universe becomes tangible again, even when the object itself remains unseen. A black hole of 66 billion solar masses does not exist in isolation. Its mass does more than curve spacetime near its center. Over long periods, it influences the structure and behavior of the galaxy that hosts it, not through forceful disruption, but through steady, persistent interaction. In the case of TON 618, that interaction is most clearly expressed through the quasar it powers. When a supermassive black hole is actively accreting matter, as TON 618 is known to have done, the energy released does not remain confined to the immediate vicinity of the event horizon. Radiation escapes. Jets and winds can form. Heat and momentum are transferred to surrounding gas. These effects are collectively referred to as feedback, and they play a central role in shaping galactic environments. Feedback is not an explosion. It is not a burst of destruction. It is a long-term conversation between gravity and matter. As gas falls toward the black hole, it heats up and radiates energy outward. That radiation interacts with nearby material, changing its temperature, pressure, and motion. In some regions, gas may be heated enough to slow further infall. In others, it may be pushed outward gently, redistributed rather than expelled. The result is regulation rather than eradication. This regulation matters because gas is the raw material of stars. Galaxies form stars by cooling gas until it collapses under its own gravity. If gas becomes too hot or too turbulent, star formation slows. If it cools efficiently and settles, stars form more readily. The energy released by an active black hole can therefore influence how quickly or slowly stars are born in the surrounding galaxy. In galaxies hosting extremely massive black holes, this influence can extend over enormous distances. TON 618's mass allows it to affect gas not just near the center, but across much of its host galaxy. The gravitational well guides the overall motion of matter, while feedback shapes how that matter behaves locally. Over time, these effects can alter the balance between star formation and quiescence. Importantly, this influence is not one-sided. The galaxy also shapes the black hole. The availability of gas, the rate of mergers, and the overall structure of the galaxy determine how much material reaches the central regions. Feedback acts as a moderating loop. Too much accretion increases radiation, which can slow further inflow. Too little accretion allows gas to cool and drift inward again. This self-regulating behavior is one reason galaxies and their central black holes appear to grow together. Observations across many systems show correlations between black hole mass and properties of the surrounding galaxy. These relationships suggest long-term interaction rather than coincidence. TON 618 sits at the extreme end of this pattern. Its mass implies that this regulatory process operated at an exceptional scale. The amount of energy involved would have been enormous, yet distributed over long timescales. Rather than a single dramatic event, the influence of TON 618 would have been expressed as a sustained presence, shaping conditions gradually. This gradualism is easy to overlook. Popular descriptions often focus on black holes as agents of sudden change. In reality, the most massive black holes tend to be the most stable. Their influence is constant, their environment responds slowly, the effects accumulate quietly, leaving signatures that are visible only when examined across millions or billions of years. In the case of a luminous quasar, some of these signatures can be observed directly. Outflows of gas can be detected through shifts in spectral lines. heating of surrounding material can be inferred from emission patterns. These observations show that energy from the central region propagates outward, interacting with the galaxy rather than simply escaping into space. Yet even here, restraint is appropriate. Feedback does not sterilize galaxies. It does not erase structure. Many galaxies with massive black holes continue forming stars. The influence is modulating rather than dominating. It shapes the pace and distribution of activity rather than extinguishing it. For TON 618, the scale of this modulation would have been significant. Its mass and luminosity suggest that its host galaxy experienced prolonged periods of interaction with its central black hole. Gas flows would have been influenced. Star formation histories adjusted. The galaxy's evolution subtly guided by a gravitational anchor at its core. All of this unfolds without intention. The black hole does not regulate its environment with purpose. It does not seek balance or disruption. Feedback emerges as a consequence of physical laws applied consistently. Gravity draws matter inward. Accretion releases energy. Energy alters surrounding conditions. The loop closes naturally. This lack of intent is important. It highlights a theme that becomes clearer as scale increases. The universe does not act. It behaves. Effects follow causes without preference. TON 618 influences its environment not because it is special, but because its mass makes certain outcomes unavoidable. This perspective reframes influence itself. Rather than imagining the black hole as an active agent, it is more accurate to see it as a fixed feature of the landscape. Matter moves in response. Energy flows according to gradients. Structure emerges from interaction rather than direction. Over long periods, these interactions leave lasting marks. The distribution of stars, the temperature of gas, the shape of the galaxy. Each reflects the quiet presence of the central mass. TON 618's role in this process is extreme, but not unique in kind. It differs from smaller black holes in degree, not in nature. The same principles apply. They are simply scaled up. This scaling matters because it reinforces continuity. The universe does not change its rules for large objects. It applies the same ones more extensively. The result is not chaos, but coherence across scales. In that coherence, something subtle emerges. As mass increases, the influence of individual processes becomes less dramatic in isolation. No single star matters. No single cloud dominates. Everything blends into long-term averages. Cause and effect stretch over time. The system becomes less responsive to small disturbances. This is where the tone of the universe shifts. At smaller scales, events feel sharp. At larger scales, they feel indifferent. Not because nothing happens, but because so much happens that individual changes no longer stand out. TON 618 exists firmly in this regime. Its influence on its galactic environment is vast but not personal. It does not create spectacle. It creates conditions. It shapes probabilities. It nudges trajectories. Understanding this prepares the ground for a broader reflection. If such an object can exist, exerting enormous influence without intention, without drama, then scale itself begins to take on a different character. The universe appears less concerned with moments and more with patterns, less focused on events and more on outcomes. This is not unsettling. It is clarifying. It suggests that meaning in the universe does not arise from action, but from structure, from the way matter organizes itself under simple rules applied across immense scales. As attention shifts from how TON 618 influences its immediate surroundings to what that influence says about the universe as a whole, a larger perspective begins to form. One where size does not imply importance, and influence does not imply intention. From here, the conversation naturally widens. Away from individual objects and toward the broader character of a universe, that allows such extremes to exist without comment. TON 618 does not exist because it was noticed. It existed long before its light reached Earth, long before instruments were built to measure it, long before anyone wondered whether it might be unusual. Its mass accumulated, its space-time curvature deepened, and its influence spread outward without reference to observation or interpretation. This is easy to forget. Much of astronomy is framed around discovery. Objects are found, named, catalogued, and ranked. Language tends to imply a before and after, as though something comes into being when it enters a database. In reality, observation is a late arrival. The universe does not wait for attention. TON 618 is a clear example of this indifference. The black hole grew to tens of billions of solar masses without being exceptional in any deliberate sense. No process selected it to become the largest known. No mechanism aimed for a record. Gravity acted, matter responded, and conditions allowed growth to proceed efficiently for long periods. The outcome was extreme, but the process was ordinary. This distinction matters. When an object appears extraordinary, there is a temptation to treat it as an exception that requires special explanation. In some cases, that is appropriate. In this case, it is more accurate to say that TON 618 represents the far end of familiar processes operating under favourable conditions. Its size is not the result of an unusual rule, but of common rules applied consistently over time. The universe does not optimize for balance or symmetry. It allows variation. Some regions remain sparse, others become dense. Some black holes remain small, a few grow very large. These outcomes are not guided, they emerge. Seen this way, TON 618 is not a statement, it is a consequence. Its mass tells a story about availability rather than intention, about gas that remained accessible, about mergers that occurred at the right times, about feedback that moderated but did not halt growth. None of these factors acted with foresight, they simply unfolded. This neutrality becomes more apparent as scale increases. At human scales, outcomes feel personal, choices matter, actions have immediate consequences. At cosmic scales, outcomes reflect averages, probabilities, and long sequences of interaction. Individual moments blur, patterns dominate. TON 618 belongs to this latter regime. Its existence does not hinge on any single event. It is the cumulative result of countless interactions spread across billions of years. Remove any one of them, and the outcome might differ slightly. The process itself would remain. This perspective shifts how size is interpreted. Calling TON 618 the largest known black hole can sound like a superlative, but the phrase carries no value judgment in physics. It does not imply importance, success, or significance in a human sense. It describes position within a distribution, nothing more. From the universe's point of view, there is no distinction between the largest and the median. Both are permitted. Both obey the same laws. Both persist without comment. This indifference is not cold, it is consistent. Consistency is what allows science to work. The same principles that describe a modest black hole in a nearby galaxy describe TON 618. The equations do not change their tone. Gravity does not behave differently because the mass is extreme. It behaves the same way over a larger region. This sameness is quietly remarkable. It means that understanding does not require attributing special status to extreme objects. It requires tracing consequences. When mass increases, space-time curvature increases. When curvature increases, influence extends. When influence extends, environments adjust. Each step follows predictably. TON 618 fits neatly into this chain. Its existence does not imply that the universe favours extremes. It implies that the universe tolerates them. Given enough time and material, familiar processes can produce outcomes far outside the average. This tolerance also means that TON 618 does not exhaust possibility. If one black hole can reach this mass without violating physical law, others could as well. They may already exist, embedded in quiet galaxies, accreting little, emitting almost nothing. Without bright quasars to announce them, they would be difficult to detect. This is not speculation in the dramatic sense. It is a recognition of observational bias. Astronomy detects what shines. Active black holes draw attention because they are luminous. Inactive ones remain hidden, their presence inferred only indirectly. The largest black holes might not be the brightest. They might be the calmest, having consumed or heated their surroundings long ago. TON 618 was noticed because it happened to be active at the time its light was emitted. That activity made it visible across deep time. It does not follow that all large black holes announce themselves in this way. This possibility reinforces neutrality. TON 618 is not a destination, it is a data point, a prominent one, but still part of a larger incomplete picture. Its significance lies in what it reveals about growth and scale, not in its status as a record holder. Understanding this keeps perspective intact. The universe does not arrange itself for ranking. It does not maintain leaderboards. Records exist only because observers impose categories. Remove the observer, and TON 618 is simply one mass among many, embedded in a galaxy, influencing its surroundings according to gravity. This does not diminish its interest. It grounds it. From this grounding, curiosity naturally turns outward. If such an object exists without intent or announcement, what else might exist beyond current reach? What other extremes have formed quietly, leaving only subtle traces? What parts of the mass distribution remain uncharted because they do not shine? These questions do not imply ignorance. They acknowledge scope. Astronomy advances by extending observation gradually, pushing sensitivity, resolution, and coverage outward. Each new instrument reveals objects that were always there, waiting only for the means to be seen. TON 618 emerged in this way, not because it appeared, but because detection caught up. Future observations will continue this process. New telescopes will survey the sky more deeply. They will detect fainter quasars, quieter galaxies, subtler motions. Mass estimates will improve. The distribution of black hole sizes will become clearer. Extremes may shift. Through all of this, TON 618 will remain what it has always been, a natural outcome of gravity acting over time, unconcerned with whether it is noticed, measured, or compared. This neutrality is not an absence of meaning. It is a different kind of meaning. It suggests that the universe does not require explanation in narrative terms. It operates according to structure, not intention. Objects do not exist to be remarkable. They exist because conditions allow them to exist. Recognizing this prepares the ground for what comes next. If observation reveals rather than creates, then the future of understanding lies not in speculation, but in patience, in waiting for light to arrive, in building instruments capable of hearing quieter signals, in allowing the universe to show more of itself on its own terms. From here, attention turns naturally toward that future, toward how observation will change, toward what may come into view next. The mass of TON 618, impressive as it already is not considered a finished number. In astronomy, no measurement at great distance ever is. Values are refined, narrowed, and sometimes adjusted as instruments improve and understanding deepens. This is not a flaw in the process. It is the process. Future telescopes will not rewrite what is already known about TON 618, but they will sharpen it. One of the primary limitations in measuring distant black holes is resolution. Current instruments collect light that has been stretched, scattered, and blended over vast distances. spectral features overlap, fine structure is lost. As a result, mass estimates rely on average signals rather than detailed motion. New observatories are designed specifically to improve this situation. Next-generation space telescopes and large ground-based observatories will be able to separate light more cleanly, detect fainter emission lines, and observe broader wavelength ranges simultaneously. This will allow astronomers to test existing mass estimates using additional tracers and independent methods. Where current measurements rely heavily on a few spectral features, future ones may incorporate many. This refinement matters most at the extremes. For objects like TON 618, even small improvements in data quality can reduce uncertainty significantly. Better resolution can constrain the geometry of the accretion disk more accurately. Improved sensitivity can reveal subtle features that help determine orientation and velocity structure. Each refinement tightens the range within which the true mass must lie. Importantly, this tightening is expected. Science anticipates revision. It does not resist it. When astronomers publish mass estimates, they do so with the understanding that future work will improve upon them. Numbers evolve as tools improve. This evolution is a sign of progress, not error. TON 618 will almost certainly undergo such revision. Its mass may be adjusted upward or downward slightly as new data becomes available. The uncertainty range may narrow, confidence may increase. What is unlikely to change is its position as an extreme object. Even substantial revisions would still place it far beyond the typical range of supermassive black holes. This expectation is grounded in experience. Throughout astronomy, landmark measurements have followed this pattern. Early estimates of stellar masses, galactic distances, and cosmic expansion rates were revised repeatedly as techniques improved. Each revision brought greater clarity without undermining the overall picture. Extremes remained extreme. Patterns became sharper. Black holes have followed the same trajectory. The first mass estimates of nearby supermassive black holes were crude by modern standards. Over time, decades of observation refined them dramatically, yet the relative ordering remained. Sagittarius A star remained modest. Giant ellipticals retained their heavier centers. Refinement clarified scale rather than overturning it. TON 618 is positioned similarly within its category. Future telescopes will also expand the comparison set. As sensitivity increases, more distant and fainter quasars will be detected. Some may host black holes approaching the mass of TON 618. Others may exceed it. If that happens, the label largest known will shift naturally without drama. This possibility is not threatening. It is expected. Science does not protect records. It updates them. The key point is that such updates occur through accumulation, not replacement. Each new observation adds to the context rather than erasing what came before. TON 618 will remain an important reference regardless of whether it is eventually surpassed. This is why patience is central to the scientific approach. Astronomy operates on timescales that do not reward urgency. Observations take years. Data analysis takes longer. Confirmation requires repetition. Discoveries mature slowly. The most reliable results are often the least rushed. TON 618 itself is a product of this patience. Its significance emerged over time, as measurements converged and uncertainty narrowed. No single observation established its status. The conclusion formed gradually, through consistency rather than surprise. Future refinement will follow the same path. As new instruments come online, astronomers will revisit existing data, compare it with new observations, and adjust models accordingly. Papers will be written, debated, and revised. Numbers will change slightly. Understanding will deepen incrementally. This process may seem anticlimactic from the outside, but it is precisely what makes the results trustworthy. In this sense, TON 618 is not a final chapter, it is a midpoint. It represents what can be known with current tools and what remains open to refinement. It sits at the boundary between established measurement and future clarity. Its mass is not frozen. Its role as an extreme object is not fixed in perpetuity. What remains fixed is the method by which understanding advances. This method values continuity over spectacle. Rather than seeking dramatic breakthroughs, astronomy builds slowly. Each generation of instruments answers some questions and reveals others. The universe does not yield its structure all at once. It allows understanding to accumulate. This accumulation is itself meaningful. It reflects a relationship between observer and observed that is not based on control or conquest, but on listening. Telescopes do not interrogate the universe. They wait for light to arrive. They collect what is offered. Interpretation follows. TON 618 was revealed in this way, not through intention, but through alignment. Light happened to reach Earth. Instruments happened to be capable of recording it. Analysis happened to be thorough enough to recognize its significance. Future refinement will continue in the same spirit. Rather than rushing to redefine what is largest or most extreme, astronomers will focus on narrowing uncertainty, testing assumptions, and expanding the sample. The goal is not to chase superlatives, but to understand distribution. This orientation prepares the ground for closure. As the story of TON 618 moves from discovery to refinement to future observation, it becomes clear that its importance does not rest on being a permanent record holder. It rests on what it reveals about growth, scale, and the universe's capacity to produce extremes without exception. The ongoing nature of science allows this understanding to remain open. It invites revision without instability. It permits curiosity without urgency. And in that openness, the narrative naturally begins to slow. Attention shifts away from what might be found next, and back toward what has already been seen, measured, and placed within context. Understanding does not end here. It simply pauses, waiting for the next set of observations to arrive. At this point, it helps to pause and take stock of what has actually been established, and where the boundaries still lie, not to heighten uncertainty, but to place it properly. Extreme objects invite exaggeration by their very nature. Stabilizing understanding means returning to what is firm, separating it from what is still under refinement, and being clear about which questions remain open because they genuinely are. Some aspects of TON 618 are solid. It exists. It is associated with an extraordinarily luminous quasar at a vast distance. The light from that quasar has been measured, analysed, and compared across multiple studies. The redshift is well determined, placing the object deep in cosmic time. The spectral features indicate gas moving at very high velocities under strong gravitational influence. These observations are not controversial, they are repeatable and consistent. From those observations, a mass estimate follows. That estimate places the black hole at approximately 66 billion times the mass of the Sun. The precise number carries uncertainty, but the scale does not. Even conservative interpretations keep the mass far above that of any other black hole measured so far. This position, at the extreme upper end of the known distribution, is robust. It is also well established that black holes grow through accretion and mergers, and that these processes were more active in the early universe. Models describing this growth have been tested across many systems and generally succeed. TON 618 does not contradict them, it stretches them. Where uncertainty enters is not in whether the object is massive, but in the details of how it became so massive so early. Several pathways remain under active study. The nature of the earliest black hole seeds is still being refined. Some may have formed from collapsing stars. Others may have originated from the direct collapse of dense gas clouds, starting life already large. Observations and simulations continue to explore which of these pathways dominated and under what conditions. Accretion physics is also an area of ongoing work. While the broad behavior is well understood, the details of how gas behaves near the event horizon, how radiation interacts with inflowing matter, and how feedback regulates growth are complex. Small differences in these processes can lead to large differences in outcome over billions of years. There is also uncertainty introduced by observation itself. Distant objects are seen through limited windows of light. Geometry, orientation, and environment all affect how signals are interpreted. These effects are accounted for, but they cannot be eliminated entirely. As instruments improve, these uncertainties will narrow. What is important is that these uncertainties are bounded. They do not allow for arbitrary reinterpretation. They do not permit the mass of TON 618 to drift down into familiar territory. They refine rather than destabilize. They operate within a framework that is already well tested. This distinction often gets lost when uncertainty is discussed. Uncertainty in science is not a confession of ignorance. It is a measure of precision. It tells us how tightly a value is constrained, not whether it exists. In the case of TON 618, uncertainty surrounds the exact mass, not the fact that it is extreme. There are also limits that come from physics itself. While there is no known absolute upper bound on black hole mass imposed by gravity alone, growth is constrained by environment and time. Accretion cannot proceed arbitrarily fast forever. Galaxies do not supply infinite material. Mergers become less frequent as structures grow larger and more isolated. These constraints explain why objects like TON 618 are rare. They do not require invoking special rules. They arise naturally from the way matter distributes itself across cosmic history. Understanding these limits helps keep perspective grounded. TON 618 is not an anomaly that breaks models. It is an outcome that tests how far models can be extended. That difference matters. One invites replacement, the other invites refinement. At the same time, observation has limits that must be acknowledged honestly. The universe is larger than what has been surveyed. Not all black holes are active. Not all massive objects announce themselves through light. Some may remain hidden simply because their surroundings are quiet. This means that TON 618 is the largest known, not necessarily the largest that exists. That statement is not hedging. It is precision. It reflects what can be said responsibly given current data. Holding this balance is part of scientific maturity. It allows confidence without overreach. It permits curiosity without speculation. It creates space for future discovery without undermining present understanding. For listeners, this balance can be calming. Rather than presenting the universe as a place of unanswered riddles or looming contradictions, it reveals a landscape where knowledge accumulates steadily. Some regions are well mapped. Others are still being charted. The edges are not chaotic. They are simply incomplete. TON 618 sits near one of those edges. It is far enough from the average to be striking, but close enough to known physics to be comprehensible. Its existence does not introduce instability into understanding. It sharpens it. This is why revisiting limits is useful. Limits define where confidence is high and where caution is appropriate. They prevent conclusions from drifting into certainty where none is warranted, while also preventing doubt from erasing what is already known. At this stage, the picture is stable. A black hole of extraordinary mass exists at a great distance. Its mass has been estimated using established methods. Its growth required favorable early conditions. Its scale stretches intuition but not physics. Its precise history remains an area of study, not confusion. Nothing in this picture demands urgency. Nothing requires resolution before understanding can continue. The universe is not withholding answers. It is offering them at a pace determined by light, distance, and patience. This realization naturally eases the tone. When knowledge is placed within clear boundaries, anxiety fades, mystery remains, but it becomes quiet rather than pressing. Questions remain open, but they are well framed. The sense of scale settles into something less overwhelming and more contemplative. From here, the narrative can slow. With the extremes acknowledged and the limits clarified, attention can shift away from analysis and toward reflection. Toward what it means to exist in a universe capable of producing such objects without disruption. Toward how human understanding fits within that larger structure. This is not a retreat from science. It is a recognition that science does not always demand forward motion. Sometimes it benefits from stillness. When confronted with an object like TON 618, it is easy for human scale to feel misplaced. 66 billion solar masses does not invite comparison. It overwhelms it. Against such numbers, everyday reference points collapse quickly. Planets, stars, even galaxies begin to feel interchangeable, reduced to vague notions of smallness. This reaction is natural, but it is not the whole story. Human beings did not evolve to measure quasars or trace space-time curvature across billions of light years, and yet that is exactly what is happening. Not through instinct, but through observation. Not through physical reach, but through inference, patience, and method. In that sense, scale does not diminish human involvement, it defines it. The mass of TON 618 is extreme, but the act of knowing it is not accidental. It required telescopes built with precision, detectors sensitive enough to catch faint ancient light, mathematical frameworks refined over centuries, thousands of observations, simulations, and revisions. Each step is small. Together they allow contact with something unimaginably distant. This is not insignificance. It is participation. The universe does not shrink to human size in order to be understood. Humans expand their reach instead, not physically, but conceptually. The gap between observer and object remains vast, but it is bridged by structure, by consistency, by the fact that the same physical laws apply everywhere without exception. That continuity is what makes observation meaningful. TON 618 does not care that it is observed. It does not change because it has been measured. But the ability to describe its mass, its influence, and its place in cosmic history is not trivial. It reflects a deep alignment between human reasoning and the structure of the universe itself. This alignment is easy to overlook when focus rests on size alone. Human scale feels fragile when compared directly to cosmic extremes. But scale is only one dimension of relevance. Another is access. Humans cannot approach TON 618, but they can detect it. They cannot experience its gravity directly, but they can infer its effects. They cannot witness its formation, but they can reconstruct plausible histories. This capacity does not erase smallness, it reframes it. Being small does not mean being disconnected. It means occupying a different role. Humans are not actors at cosmic scale. They are interpreters, witnesses, participants in the sense that they are part of the same physical system, governed by the same rules. The atoms that make up a telescope, a detector, or a human observer obey the same laws as the gas spiraling into TON 618. Gravity curves space-time for both. Light carries information from both. Time advances for both, though at different rates under different conditions. This shared framework matters more than relative size. TON 618 is vast, but it is not alien. It does not require a different kind of physics to exist. Its behavior is an extension of familiar principles applied patiently over time. That patience mirrors the way understanding itself develops. From this perspective, observation becomes a form of dialogue rather than domination. Light leaves the quasar. It travels across expanding space. It arrives at Earth. Instruments receive it. Analysis extracts meaning. Nothing is forced. Nothing is taken. Information is exchanged through natural processes that were already in motion long before observation occurred. This exchange is quiet. There is no dramatic moment where the universe reveals its secrets. There is only accumulation. A spectrum here, a redshift there, a model refined, an uncertainty narrowed. Over time, an object like Ton 618 becomes less abstract. Not because it becomes smaller, but because understanding becomes deeper. This depth is grounding. Rather than leaving humans feeling overwhelmed by scale, it situates them within a continuous chain of cause and effect. From early cosmic conditions to galaxy formation, from black hole growth to quasar emission, from ancient light to modern detectors, each link connects naturally to the next. In this chain, human presence is not disruptive, it is receptive. That receptivity is often mistaken for passivity. In reality, it requires effort, discipline, and restraint. Knowing when not to speculate, knowing when to revise, knowing when to wait for better data. These are active choices, guided by respect for evidence rather than desire for certainty. Ton 618 highlights this approach. It invites awe, but not urgency. It encourages reflection, but not resignation. Its mass is overwhelming only if taken as a statement about importance. Taken instead as a statement about possibility, it becomes clarifying. The universe is capable of producing structures far beyond human scale without strain. It does so routinely, and yet those structures remain comprehensible in principle. That comprehensibility is not guaranteed. It is a feature of the universe that happens to align with human cognition. This alignment is subtle, but profound. It suggests that understanding is not about matching scale, but about matching structure. Humans do not need to be large to understand large things. They need consistent rules, reliable signals, and time. Ton 618 provides all three. Its existence follows predictable laws. Its light carries measurable information. Its story unfolds across timescales long enough to be reconstructed. Nothing about it is hidden behind mystery for mystery's sake. What remains unknown does so because observation has limits, not because meaning is withheld. Recognizing this helps ease the emotional weight that extreme scale can bring. Instead of feeling dwarfed, it becomes possible to feel situated. Not at the center, but not excluded either. Humans occupy a small region of space and time, but they are connected to the rest through physical continuity. This continuity allows questions to be asked without anxiety. What else exists beyond current detection? How many similar objects formed early? Whether Ton 618 is rare or simply the brightest example of a broader population, these questions are not unsettling. They are natural extensions of what is already known. As the narrative approaches its end, the emphasis shifts again. The purpose is no longer to analyze mass, growth, or influence in detail. Those foundations are in place. What remains is to acknowledge the position from which this understanding arises. Humans observe from one planet, around one star, in one galaxy. That position is not privileged in a cosmic sense, but it is sufficient. From there, with careful instruments and disciplined reasoning, it is possible to engage with objects like Ton 618 meaningfully. This engagement does not require emotional amplification. It does not require drama. It requires attention. Attention is the quiet counterpart to scale. Where scale expands outward, attention focuses inward. Together they balance. TON 618 is vast. Human attention is narrow. Yet it is through that narrow channel that the vast becomes known. This is not a paradox. It is a relationship. And as that relationship settles into place, the tone naturally softens. The extremes have been traced, the limits acknowledged, the questions framed. What remains is not urgency, but perspective. From here, the conversation can rest. The facts do not need to be pushed further. The universe does not need to be pressed for answers. It has already offered enough to reflect upon quietly. The presence of TON 618 does not demand a conclusion. It allows one. A conclusion not about dominance or insignificance, but about coexistence within a universe large enough to hold both extreme mass and thoughtful observation without contradiction. By this point, TON 618 no longer needs to be introduced or justified. It has settled into place as a reference point, not because it demands attention, but because it quietly earns it. Its mass, its distance, its timing and its effects have been traced carefully, each from a different angle, each reinforcing the same general picture without repetition or exaggeration. What remains is not a list of facts, but a shape. TON 618 exists at the far edge of what has been measured so far. Its mass, estimated at tens of billions of solar masses, places it well beyond the familiar population of supermassive black holes found in nearby galaxies. That alone makes it notable. But the deeper significance lies in how unremarkable the processes behind it turn out to be. Nothing about its existence requires a special rule. Accretion behaves as expected. Mergers follow known dynamics. Gravity curves space-time predictably. Light carries information faithfully across billions of years. When placed together under favourable conditions, these ordinary ingredients produce an extraordinary outcome. TON 618 is not a contradiction. It is an extension. That extension matters because it marks a boundary rather than a conclusion. It shows how far known processes can be pushed before explanation begins to thin, not because the rules stop working, but because observation becomes more difficult and timelines compress. Its mass challenges intuition, but not physics. Its timing strains growth models, but does not break them. Its influence reshapes its environment, but does so calmly, without drama. In this way, TON 618 acts as a marker. It marks the upper edge of current measurement. It marks the effectiveness of black hole growth under early cosmic conditions. It marks the point at which language becomes less helpful than numbers, and imagery gives way to abstraction. It marks where comparison loses clarity, and scale becomes something to acknowledge rather than conquer. Markers are useful precisely because they are not endpoints. They do not say that nothing lies beyond. They say that something definite lies here. They give structure to exploration, allowing progress to be measured without implying completion. TON 618 fulfills this role naturally without being assigned it. Its discovery did not close a chapter. It clarified one. Before objects like this were measured, it was uncertain how massive black holes could realistically become. Models allowed growth into the billions of solar masses, but evidence beyond that was sparse. TON 618 demonstrated that, under the right conditions, growth could proceed much further. That realization sharpened questions rather than answering them completely. How common are such objects? How early did similar growth occur elsewhere? How often did early environments align in this way? Each question remains open, not because of confusion, but because observation has not yet reached far enough. This openness is deliberate. Astronomy resists the temptation to fill gaps prematurely. When data is limited, restraint becomes part of accuracy. TON 618 benefits from this restraint. Its role is not inflated beyond what evidence supports. It is allowed to be large without being definitive. That balance is what gives it lasting value. Even if a more massive black hole is discovered in the future, TON 618 will not lose relevance. It will remain a point of comparison, a benchmark against which new extremes are evaluated. Its contribution is not erased by succession. It is incorporated. This is how science accumulates rather than replaces. Each object adds resolution to the overall picture. Extremes define range. Averages define pattern. Outliers reveal structure. TON 618 contributes to all three, depending on perspective. Viewed statistically, it sits at the far tail of the distribution. Viewed physically, it demonstrates what sustained growth can achieve. Viewed historically, it shows how early cosmic conditions could support rapid accumulation of mass. Viewed observationally, it highlights both the power and the limits of current instruments. None of these views requires emphasis over the others. Together, they form a stable understanding. As the narrative slows, it becomes clear that the most important feature of TON 618 is not its size alone, but its placement within continuity. It does not stand apart from the universe. It belongs to it fully. Its extremeness does not isolate it. It integrates it more deeply into the broader story of structure formation. That story is not linear. It does not progress neatly from small to large, simple to complex. It branches. It varies. It allows for rare outcomes alongside common ones. TON 618 occupies one such rare branch, but it grows from the same trunk as everything else. Recognizing this removes the need for final statements. There is no requirement to decide whether TON 618 represents a limit. There is no need to frame it as a culmination. Doing so would impose a human desire for closure onto a process that does not operate that way. Instead, it can be allowed to remain what it is. A well-measured object at the edge of current knowledge. A confirmation that known physics remains reliable even when stretched. A reminder that the universe does not privilege moderation. It allows extremes when conditions permit. This allowance is quiet. TON 618 does not announce itself with violence or spectacle. It does not dominate headlines because it seeks attention. It sits, distant and steady, its significance emerging only through careful work. That steadiness mirrors the way understanding itself develops, slowly, incrementally, without urgency. As attention eases, the tone naturally decelerates. There is no need to press further. The facts have been laid out. The limits have been acknowledged. The implications have been explored. What remains is not a conclusion in the traditional sense, but a settling. The image of TON 618 does not linger as a visual. It lingers as a scale reference, as a number that resists intuition but fits cleanly into equations, as an outcome that feels vast but not threatening, as evidence that the universe can accommodate extremes without instability. This settling prepares the ground for closure. Not a closing of inquiry, but a pause in narration. A moment where the object can recede slightly. Not because it matters less, but because its place is secure. Understanding does not need to push further to be complete enough for now. From here, attention can drift outward again, toward the broader universe, toward the act of observing itself, toward the quiet fact that such objects exist whether or not they are being discussed. TON 618 remains where it has always been, distant, massive, indifferent to attention. What has changed is not the object, but the clarity with which it can be held in mind. That clarity does not demand excitement. It invites calm. And with that calm in place, the narrative can step gently toward its conclusion, carrying forward not a sense of finality, but a sense of proportion. TON 618 does not ask for interpretation. It does not invite fear, symbolism, or metaphor. It exists, and that is enough. A black hole with tens of billions of solar masses sounds dramatic only when language strains to keep up. In physical terms, it is simply an arrangement of mass and space-time that follows the same rules as everything else in the universe. Gravity curves, matter responds, light carries information. Nothing about this object behaves with intent, urgency, or spectacle. It is not dangerous in a narrative sense. It is not looming. It is not watching. It is distant, steady, and entirely unconcerned with being noticed. What makes TON 618 meaningful is not that it threatens understanding, but that it quietly exceeds intuition while remaining fully consistent with what is known. It shows that reality does not need to fit human scale in order to be real, and that comprehension does not require comfort. There is a temptation, when faced with extreme objects, to frame them as warnings or symbols, as reminders of insignificance, as evidence of chaos or hostility. TON 618 does not support any of those readings. It does not diminish human relevance. It does not suggest that the universe is violent or indifferent in a moral sense. It simply demonstrates that scale is not calibrated for human experience. Understanding does not mean controlling. It does not mean standing above what is observed. It means placing something accurately within a wider structure and accepting the limits of what can be felt or visualized. TON 618 has been placed. Its mass has been estimated with care. Its distance has been measured. Its influence has been traced through light that left its source billions of years ago. Each piece of information rests on observation rather than assumption. Each has been refined rather than dramatized. Nothing about this process required mastery over the object itself. No proximity was needed, no intervention. Understanding emerged from patience, comparison, and consistency. That approach matters. It shows that knowledge does not depend on reducing the universe to human terms. Some objects will always exceed intuition. Some scales will never feel familiar. That does not place them outside understanding, it simply places them outside imagery. TON 618 is one such object. It cannot be imagined clearly. It cannot be held mentally in any satisfying visual form, but it can be described, measured, and placed within a coherent picture of how the universe behaves. That picture remains stable even as individual numbers are refined. In that stability there is calm. Nothing about TON 618 suggests urgency. It does not demand answers beyond what evidence supports. It does not force conclusions about limits or endings. It stands as a reminder that the universe allows outcomes that feel extreme without breaking its own structure. That allowance is quiet. Black holes do not mark turning points. They do not serve as punctuation in cosmic history. They accumulate, persist, and fade from activity according to circumstance. TON 618 is no exception. It does not announce itself as special. It simply occupies a position far out on a distribution that extends.